So the last talk at the conference is by Iñaki Garcia-Etxebarria. He will tell us about symmetries from string theory.
All right, thank you very much. And thank you to the organizers for putting together such a nice conference. And thank you for inviting me to speak on it. So I want to discuss how to obtain the kind of symmetries that Kantara was discussing, at least in some cases, in string theory. I will do the basic case of generalized symmetries without saying much about invertible symmetries, although I think we now understand how to do this too. So this is based on papers with Ben and Diego, and a more recent paper with Fabio, Federico, my student Sagar, and Sakura. So this is a talk about geometric engineering. I will view string theory as a tool that gives me, given a geometry, a quantum field theory. And I want to understand how to extract the symmetries of the field theory from the geometry. In particular, I will want to construct this object that Kantara already alluded to, this symmetry TFT. I will explain what this is. This is an object that will encode the symmetries, the anomalies, and the gaugings of the symmetries for the local dynamics on the singularity. And it turns out that even if the field theory itself is hard to understand, the symmetry TFT is much easier to construct. It's both easier to understand and easier to construct. So generally, when you want to understand the theory, understanding the symmetries is a good first step, and this is good news. You can understand the symmetries much earlier than the full theory itself. So whenever you have a Lagrangian, of course, you don't have to go through such contortions. You can look at the Lagrangian, the degrees of freedom, and if you are clever enough, you can understand all the symmetries of the theory. So Tom and Kantara already gave very beautiful reviews of how to read symmetries in some theories, these generalized symmetries. So I won't review things again. I just want you to keep in mind that the most important point, that these days we think of the word symmetry as meaning topological operator in your theory. So there has been lots of progress on this, and many beautiful talks in the conference. But I want to go in a slightly different direction, because when you're doing geometric engineering in string theory, having a Lagrangian description of your quantum field theory is a luxury that you very often don't have. You know the geometry, but you don't know the Lagrangian. And it is precisely in the cases that you don't know the Lagrangian that the symmetry information is the most important, because very often you don't know almost anything about the theory. So having the having the symmetries is an excellent first step. So for example, you can use the symmetries to suggest ideas for dualities or to test dualities if you have some ideas. Okay. Another reason that I care about this problem is that it hints towards a geometric version of the Landau paradigm. So generally you say that if you know the symmetries, can you reconstruct the theory? Well, here you can say something a little bit more precise. Here what you will try to do is, if you know the sim TFT, I'll describe in a second how to obtain it. So if somebody hands a sim TFT to you, can you reconstruct the string background in which the theory started from? And of course, this is all modulo dualities and deformations. But I guess a bit more precise setting in which to formulate this question. So Shlomo had a great review on Tuesday of what we know and what we don't know about field theories in diverse dimensions. So in terms of his analogies, I guess I'm asking if somebody hands you the skull of some animal, can you recognize which animal it is? Sometimes you can. So although I won't go into category theory, I'm learning it, so I shouldn't give a talk about it. But this seems to be the right framework in which to formulate these kind of things. And we have already made a little bit of progress in this direction, trying to answer this kind of question in a categorical language. So I just point you to these two papers that we wrote, basically following up on work by Garcia and Cecotti. But I won't talk about category theory today. Okay, so as usual, if you're doing a string engineering, you want to put some constraints on the geometries that you consider so you can understand them. I'll take sort of the standard, simplest constraints. So first of all, I want to engineer quantum field theories. So I'm going to take my manifolds to be non-compact. That's because I don't want to couple to gravity. I want a CFT in 5, 6, 4 dimensions. And to make life simpler, this is not a requirement, but I will just assume it to make things easier. I will assume that X is some sort of cone over some base. In order for the field theory to be supersymmetric, I will also assume that, as usual, X is Calabi-Yau or something like that. In the simplest case, the one that we'll discuss in the talk, X is on complex twofold. So if you ask about non-complex twofolds, well, you have C2 mod gamma, with gamma a subgroup of SU2. So this is a cone. It's a cone over S3 mod gamma, with the gamma acting freely. So the base of the cone is not singular. On SIF2 itself, you have a singularity at the origin, and it's in the singularity that the field theory lives. But we want to look far away from the singularity to extract the symmetry structure. Okay, so one of the theories that you can construct in this way, which is very interesting, is the 2,0 superconformal field theory in 6 dimensions. So this comes about by putting type 2B string theory on this kind of geometry. And it's believed that all the theories that exist of this form, 2,0 in 6 dimensions, are labeled by the subgroups of SU2. So you give me an algebra of type A, D, or E, and this defines a theory in 60. And we can engineer all of this. So one important property of the 2,0 theories with algebra G is that you put them in a torus and you get, and the torus has complex structure tau. It gives rise to a 4D n equal to 4 super mills with algebra G and complexified gauge coupling tau. So we'll call this thing I just constructed G4. And I'm not saying that this is an equal to 4 theory, because this will be a slightly imprecise language. The information I have given you so far is enough to specify the behavior of local operators, but it does not fully fix the theory. So one thing that you can compute, and I haven't told you enough to be able for you to compute it, is the partition function on compact manifolds. So I ask you to compute the partition function of this theory on K3. You cannot do it yet. So this is a standard example. If the algebra is SU2, I haven't really told you if you should sum over SU2 bundles or all SO3 bundles, and the partition function is different. These two choices are both consistent. We are talking on equal to 4. The matter is in that joint, so you can choose either consistently. The dynamical matter doesn't make a choice for you. Okay, so this is well known. This is very old. The standard thing that you'll do at this point is say, yeah, okay, I don't know this information, so you have to tell me some extra choice, the global form of the gauge group. And in this way, you define a proper 4-dimensional theory. So I want to do something slightly different. And I want to do this because this is really the way that the string theory thinks about these sort of singularities. We'll think of G4 itself, so the theory that only includes the local data, as a relative theory. Frida and Telemann introduced this language and did a beautiful analysis of this topic. So in physical terms, what you really have is a 5D theory on a semi-infinite interval, and your G4 lives on a boundary. But it's not quite a 4-dimensional theory yet. It's a 5-dimensional theory on a boundary. The thing that attaches to your boundary degrees of freedom is what we call the symmetry TFT. So in this language of relative field theory, we'll say that G4 is relative to the sim TFT. So this object here, even if it's gapped, so it's a fairly simple theory, but it includes all the information, well, includes information of the symmetries, the anomalies, and the gaugings of all the theories with this somewhat local dynamics. Okay, and I should say there's a small exception to what I said. I don't know how to include the Weil symmetry in non-supersymmetric cases in this context. Somebody has an idea, I'm happy to talk. But everything else I know, I think it fits in this framework. So as I mentioned a few times, this object is much easier than this one in general. It's a gap theory, it's a topological theory. You can understand it quite well. In fact, for things like SUN, it's a really simple theory. The most interesting part of this is just a set n gauge theory or something with this action. It's a very simple object. Of course, in the end, you want a 4-dimensional object. Well, or you might not, but if you want a 4-dimensional object, the thing that you need to do is introduce a gapped interface. Another one, this raw line here, which is an interface, between the SimTFT and a simpler theory, which is known as the anomaly theory. This is an invertible topological field theory. So this is another way of saying that if you forget about anomalies for a second, you can define a 4-dimensional theory by starting with this local construction, which is really a 5D theory, but adding a gap boundary. Your choice of gap boundary here is the choice of global form, and to construct a proper 4-dimensional theory, what you do is you collide these two domains here. Okay, so the choice of global form for us is the choice of rho. So in a different language, this was done by Haronisawa and Tachikawa. They classified for us all the rows that we can put. But of course, we weren't talking about this language of the SimTFT. In fact, this language, as Kantar already mentioned, this is sort of the topological sector of ADS-CFT. So Witten already constructed the right SimTFT for SUN holographically in this paper. And we did the D and E cases in this paper with Diego and Ben. Okay. So This is all well and good, but that's not what we have, right? We started with type 2B on this kind of geometry. So we had our ALE space. It has a singular point, 2,0 lives on this singular point, and then we compactify the torus to give us a 4D theory that we put further in some 4 manifold. So n equal to 4 theory lives on M4. So how do we obtain this symmetry TFT, this theory that encodes the symmetries of our theory, from the string theory perspective? That is where is SymTFT in the string construction. And that's what I'm going to do now. And importantly, even if this is a Lagrangian theory, I'm not going to use any knowledge about the n equal to 4 case. The same techniques apply, and we have applied it to theories where we don't know the Lagrangian. Okay. So let's start with the standard discussion. These are generalized symmetries. The object charts are typically extended operators. So let's try to see where the extended operators are. Well, in this particular case, they are heavy branes, infinite heavy branes, that look like this. There's a non-compact brane that ends on the singularity. This non-compact brane has infinite mass from the point of view of the field theory, and it becomes a defect, like a Wilson line or a Toff line or something like that. So these are my charged objects under the higher form symmetry, but they're not topological, so they're not symmetries. The things that actually measure the charge, the things that measure if you have inserted these objects or not, will be the integral of, say, a Ramon-Ramon flux, if you're doing type 2B, in some cycle that links the defect, and then you'll measure some flux. So if you want to see if you have a D3, what you surround the D3 by some cycle and integrate F5 in there. So this is the kind of thing that you're doing here. Okay, so these are my symmetries. And here comes the subtle point. So to fully specify the string background, you don't need to just give me the geometry. You have to give me also what happens to the flux configuration at infinity. As in any time when you do the path integral in quantum gravity, you have to specify the boundary behavior. Okay, so this is the cartoon of what we have. Let's keep track of things. So we have some sort of cone and a field theory that lives in d dimensions, the small d. And we start with type 2B, where big D is 10. So we have a cone, which is of d minus d dimensions, and this cone has a base. So what I'm going to do to specify the boundary behavior here is to quantize the system, taking the radial direction of the cone as time. So it's going to take my spatial dimension to be my spatial slice when I quantize to be the base of the cone times the space-time where the field theory lives. Okay? And in doing this, I will be able to specify what happens to the fluxes at infinity. That's what I want to learn. So, of course, quantizing string theory is very difficult if I want to do it completely, but all I need to do is understand the fluxes, and that's significantly easier. What I have is a generalized Maxwell theory, schematically. So I have some P form, CP, and it has an action, which is F, which F, star F, as usual. Whenever you have this kind of abelian field theory, Cantor already mentioned that you can have flux operators, so operators that measure the flux. And for my purposes, it's good to parameterize these operators in the following way. So you have things that measure the electric flux, and they're parameterized by a class in HP. Remember that P is the degree of the P form that I have in my generalized abelian case, with coefficients in U1. So R mod Z here just means U1 in a fancy way that's sort of more appropriate in this context. And similarly for the magnetic case. So this might be a little bit unfamiliar. So let me spend 1 minute trying to review why this is true. Imagine that there's no torsion in your manifold, where you're quantizing the field theory in MD-1. Then this group here is simply the standard cohomology group in any degree K. So K will be P or D minus P minus 2. Is the standard cohomology group times U1. Now, if you do Poincare duality here, what you have is some homology group. This one times U1. That means I have a cycle of this dimension and a U1 coefficient. So, for example, if I'm doing the magnetic charge, which is parameterized by this cohomology group, and I put K equal to D minus P minus 2, this exponent here, I get that my flux operator becomes exponential 2 pi I times alpha, the U1 coefficient, times the integral over the cycle that I have here of the integral of the flux. So this is a standard Gukov-Witten operator, but written in a way that works also with torsion. Right? This is in the case that there's no torsion, but if you have torsion, this expression is still true. Okay. So that's fine. That's how the operators that you have. And Moore and then Fried, Moore and Segal showed that these flux operators in general don't commute. Electric and magnetic charges don't commute in abelian theory. It's a surprising statement, but it's true. The commutation the non-commutation rather happens whenever you have torsion in your manifold. So there's a map beta, which is called the Bockstein. Details are not important, but it extracts the torsional part of this class I just constructed. So it's precisely the one I didn't talk about before. And there's a linking pairing between the torsional components of the cohomology. Again, the details don't matter. The thing that matters is that the operators that measure the flux at infinity do not necessarily commute whenever there's torsion. And that's generic. There's very often torsion. So whenever you have things that don't commute, you cannot simply turn off all fluxes at infinity. Turning off fluxes, remember that my flux operator was roughly the exponential of the integral of f. If I want to turn off the flux, means setting this operator to 1. But you have a commutator, these two get a minus sign when you exchange them. You cannot set both of them to 1. So you have to make choices. So, all right, you can then do this thing carefully, and with this, with Ben and Diego. And we show that if you look at all the possible choices at infinity in the string construction, you reproduce the prescription in Haroni-Seiberg and Tachikawa. And as I mentioned before, this is good because now I can do this for any theory. I didn't use any information on n equal to 4 here, just the geometry. So this philosophy is very general, and it explains and predicts high-form symmetries of geometrically engineered quantum field theories in many settings. There's different ways of doing this. This is not the only one. So Gigi has a beautiful paper where he explains how to obtain high-form symmetries from classes, in the case without punctures. And these authors, so Michele, Jonathan, Daniel, and Tom, had a sort of direct translation of the paper by Haroni-Seiberg and Tachikawa. By now, there are many, many cases. This is a very active field in the last couple of years where people have understood how to do these kind of calculations in a lot of generality. And I emphasize that not all cases are understood. So one case that initially I cared about, I still care about it, is n equal to 3, and we haven't solved it yet. So you can do many things, but you cannot do everything yet. So all these approaches are, of course, quite related. You can translate a calculation in one approach to a calculation in a different approach. But the one I'm presenting with these non-commuting fluxes connects very well with this symmetry theory that I want to explain now. Okay. So I just argue that in geometric engineering, whenever you are engineering a quantum field theory in a singularity, it's not really completely isolated because you always have this topological sector coming from the fluxes that doesn't decouple. No matter how far in the IR you go, these flux operators still don't commute. The commutator doesn't depend on the RG scale. So it doesn't completely decouple, but the way it doesn't completely decouple is easy to understand. It's because of this effect of flux non-commutativity. So we can think of this as having a d-dimensional field theory coupled to a d plus n-dimensional topological bulk with n bigger than 1. But the discussion in Telemann and Fried of relative quantum field theory applies in the case that you have a theory in d dimensions and you go 1 dimension higher to construct the symmetry TFT. So the question is there a way of connecting what I just explained in terms of fluxes with the construction of Fried and Telemann? So some topological field theory in 1 dimension higher. So let's consider, let me change the example slightly a bit because this one's a bit easier to explain. Imagine that you have M theory on some 7-dimensional manifold times this kind of ALE space. And let's try to understand how the topological field theory arises in 1 dimension higher. So I remember that what I was doing was quantizing on the base of the cone. So, and everything is topological. So instead of thinking of this picture, which is the actual geometry that I have, because everything is topological, let's think of this picture instead. I have sort of deformed the cone into some sort of cigar with the same base, but now asymptotically goes to the same, it goes to a constant size. So this suggests a strategy when you look at this picture, if you want to go from this picture to a theory in 1 dimension higher only and not 4 dimensions higher. Well, there's sort of an obvious thing that you can try, which is integrating over the base of S3 mod gamma to get something 1 dimension higher. So this is what we did in the paper here with Fabio, Federico, Sagara, and Sakura. And it was to do the integration over the base, basically. All right. So it has kind of two parts, what you get from integrating over the base, the SymTFT. One of them is a BF theory, sort of discrete gauge theory, which is the most interesting part, perhaps. So in the full theory on here, you have non-commuting flux operators. In this case, just to be able to draw pictures, I switched to homology, although I emphasized before that cohomology is in general better, but it's harder to draw. I don't know how to draw it. But homology I can draw. So if I Poincare dualize, I can think of operators that wrap a one cycle in S3 mod gamma and a two cycle in M7, the spatial slice. And similarly, one cycle in here and a 5 cycle in here. So if you follow the Poincare derivatives, these are the degrees that you get. And you can compute that the commutation relation of these flux operators, parameterized in this way, goes with the linking pair in S3 mod gamma. So these are one cycles in S3 mod gamma, so the link, or the can link. And then the intersection product in M7. These two things intersect in M7. So let's take set M for concreteness. In this case, the linking pairing is 1 over n. You can go and compute it for the generator of H1 with itself. So from the point of view of the effective field theory, we have a set n, 2 surface operators and 5 surface operators. And the relative phase, when you try to commute them, goes with the intersection modulo n. So this is precisely the operator content of the 8-dimensional set n theory with topological action here. Okay, so you can look at the spectrum of operators, you see how they commute or they don't commute, and by uplifting to higher dimensions, you understand which effective field theory you have in 8 dimensions. So in this way, you can extract the field theory. It's a little bit clunky. It will be nicer to do some sort of reduction, like an integral. And we do that in a paper. Well, we are going to publish a paper with Sagar, where we do this more directly from ideas of Beloff and Moore. Okay, you also have mixed anomalies. So in 7 dimensions, in addition to the 1-form and 4-form symmetries that act on Wilson lines and Toth surfaces, you have a 2-form symmetry, the instanton symmetry. And this is a mixed Toth anomaly between the U1 instanton symmetry and the 1-form symmetry of this form. So let me try to explain what's going on here. C3 here is the background for the instanton symmetry. You take the derivative, you get the field strength, so it appears here. This thing here is the Pontryagin square. It means, think of it simply as B2 squared. I'm just writing it in a bit more general way, but it's just B2 squared, essentially. And then there's a coefficient here. So B2 is the background for the 1-form symmetry, and there's a coefficient here that you need to compute. Okay, so there's a mixed anomaly, meaning that whenever you turn on a 1-form symmetry background, it can acquire instanton charge. So this is a very subtle phenomenon, but it happens in 4 dimensions and higher. So we could derive this coupling in the following way. We take the M theory action, the topological sector here, and we integrate it on S3 mod gamma. And by the way, there's a very beautiful paper by Miriam and collaborators where they do something very similar. So mathematically, we want to extract a discrete cohomology invariant in D+1 dimensions from the Chern-Simons coupling here. But this is a bit problematic, at least when you start, because first of all, C3 is not globally well defined. Here with torsion, you have to worry about global phenomena. And G4 is equal to 0. So you have something that's not globally defined, which product with something which is 0. And you're expected to get something which is different from 0. You're expected to get basically this RG mod 2. But these problems really cancel each other. If you make sense of this in the right way using differential cohomology, you can compute it, and then the answer is non-zero. So I won't give details, but if anybody's interested, I'm happy to do so. So here's the final answer. You get this coupling here, which is basically my F4 before, the background for the 2-form symmetry, and field strength, the B2 squared, and then a coefficient, which very interestingly, and I haven't found this formula in the literature before, but I find it very pleasing. This is RG mod 2. This was computed before using field theory methods, but geometrically you can reinterpret it as a Chern-Simons invariant on this kind of lens space. So it's a rather pretty formula, I think. Anyway, you can do the same thing in 5D, and you can do many things. But let me close by explaining some kind of more general things that you can do, which are not just more of the same. So you can do two groups. This is an area that has been very active recently. There are many papers explaining how to obtain 2 groups in field theory. And we can also understand this geometrically now, since a few months ago. And they follow from some interesting vibration structure in homology and the base. But we don't quite have a SymTFT description in this way. Non-invertibles is even more recent. Cantero gave a great talk about this. It's interesting that you get this kind of structure, so you multiply the operator with itself, and instead of giving you 1, it gives you 1 plus something times the condensations that Cantero was talking about. So very recently with Ben and Sakura, we also understood how to do this. In particular, condensations are fun to see how they appear in string theory. But anyway, let me close. So for geometrically engineered theories, there's a close connection between the symmetries of a theory and the geometry, but crucially, the symmetries are much easier to compute. What I showed you is technical, but it's doable. And many other properties of the theory are just not doable with the level of technology that we have right now. And this is particularly so for non-Lagrangian cases. And I have focused on the developments I understand best, but there's a lot of beautiful things that I could have explained that are also really nice. For example, there's a lot of nice papers about anomaly in flow. Ivo and collaborators have some nice papers on this that it will be good to incorporate into these settings. And I want to emphasize that this is a bit of an adventure, so we don't quite have a full systematic dictionary yet, but we're starting to get a kind of big picture, and it's really nice. Thank you.
Thank you very much. Are there questions?
You had this symmetry topological field theory, and you assume that it has a gapped boundary.
Yeah.
That's not always the case.
It's true, that's not always the case. For the ones that we have that appear in these settings, we don't know they have gap boundaries, but in the general case, we don't know.
Other questions?
There's a question back there.
Thank you for the talk. You went a little bit fast at the end, like by the part of the non-invertible symmetries. Can you comment a little bit more on that?
Yes. I was being very sneaky here. Yeah, I can comment a little bit more on that. So the thing that we did here, there's different constructions that people have done for non-invertibles. So here we're focusing on one that, somewhere here, I think in this paper, Sakura and collaborators constructed for the SO and spin theories. That's the case where you understand the non-invertibles and you have a holographic setting. So what we understood is what these operators are in string theory in the holographic sense, and why when you take two together, they give you these terms and condensations. I'm happy to explain offline if you want to. Yeah.
More questions? If not, then I think this is the end of the talk part of the conference. So let's thank Iñaki again.
Okay.
And maybe I take this as an opportunity to make a few comments and remarks. I think I'm not speaking for myself when I say that this conference will probably be remembered for several reasons. The first and foremost reason being that it happened at all. Second reason is that it happened in such a nice city and such a nice university. Third reason is, of course, all the scientific results which were presented, but this will be reviewed by Hiroshi Oguri in the next. And then finally also for the very smooth organization that I think many people were involved. We saw some of them in these red T-shirts, and others are sitting here in the front row, but there are many more. And I think we should give them a big hand. We have the last coffee break.